Hey everyone, welcome to this explainer. Okay, today we're diving into something we all think we understand, but honestly, very few of us actually do. We're talking about the incredible underlying physics of weight loss. We're going to break down this absolutely fascinating biohacking experiment by computer scientist Andrej Karpathy. Over a year, he basically decided to treat his body exactly like a machine, or really a computer, just to drop from 195 pounds down to 165. But he didn't just want to lose the weight, right? He wanted to understand the absolute biological and chemical mechanics of exactly how his body powered itself. And what he found out? It is absolutely going to change how you view your own metabolism. So, to kick things off, let's look at this central mystery of the missing mass. It's a super simple question, but it literally stumps almost everyone. Think about it, your body weight is just the total sum of the individual atoms that make you up, right? Carbon, hydrogen, nitrogen, oxygen. So let's say you weigh 180 pounds one day and then 178 pounds the next. Where did those 2 actual pounds of physical atoms go? I mean, they can't just magically evaporate into nothingness. If our bodies could literally turn mass into pure energy, we would literally be nuclear reactors. So, where does the fat go when you quote-unquote burn it?
Well, the mind-blowing answer here is that you literally breathe it out. Yeah, you heard me right. 84% of your fat loss is exhaled as carbon dioxide right into the atmosphere. The carbon atoms in the CO2 you just breathed out, they might have been part of a fat cell in your body just seconds ago. It is just wild to think about. Every single time you exhale in a fasted state, you are literally breathing out your fat, carbon by carbon.
Okay, let's really dive into this. To understand how on Earth we breathe out fat, we've got to look at the body's ultimate currency. Meet ATP, or adenosine triphosphate. You see, regardless of what you eat or what kind of energy your body has stored away, your body discharges its batteries for one single, completely unique purpose: to make ATP. It basically acts as this universal $1 bill that pays for almost every piece of work your cellular machinery does. Whether you're moving a muscle, transporting molecules, or just firing the neurons in your brain right now to watch this explainer, ATP is the currency paying the bill.
And the way ATP works is just an absolute mechanical marvel. Your body takes this molecule called ADP, which only has 2 phosphate groups, and it literally snaps a 3rd phosphate group right onto the end of it. Doing this is the molecular equivalent of squeezing and loading a mechanical spring. When your cells need energy, snap. They quickly break that 3rd phosphate off, releasing the energy to do the work and leaving that ADP behind to be reloaded. So, breaking down the food you eat, it just provides the energy to continuously load millions of these tiny molecular springs over and over again.
Now, what's really interesting here is how we can map the body's energy storage directly to a computer's memory hierarchy. Remember, Karpathy is a computer scientist, so if ATP is the immediate energy, how do we store the backups? Well, first we've got the phosphocreatine system. In computer terms, think of this as your L1 or L2 cache. It is incredibly local, it's super fast, but it has a really tiny capacity. It's just meant for those immediate sudden bursts of energy that last maybe a few seconds.
Next up, we have glycogen. This is basically carbohydrates stored up in your liver and skeletal muscle. And this acts exactly like a computer's RAM. It's your short-term memory. It stores about 2,000 kilocalories, which is enough to power your body for roughly 24 hours. But here's the catch. Glycogen isn't a very dense storage medium, and more importantly, it acts just like a sponge. It binds heavily with water, like about 3 grams of water for every 1 gram of glycogen. We're actually going to come back to this sponge effect a bit later, because man, does it create a lot of confusion when you step on a scale.
And that brings us to our ultimate long-term storage, adipose tissue, or as we usually call it, fat. In our computer analogy, fat is your hard disk drive. It's a high-latency, massive capacity storage system. Sure, it takes a bit longer to access because the fatty acids actually have to be shuttled through the bloodstream, but the storage potential here is massive. Our bodies just eagerly stockpile this fat to keep us alive in case food ever becomes scarce.
To truly grasp the sheer scale of this biological hard drive, just look at this number: 678. When Karpathy started his experiment, he carried about 40 pounds of fat. And because fat is so incredibly energy-dense, at 9 kilocalories per gram, that 40 pounds contain the energetic equivalent of 678 sticks of dynamite. Let that sink in. If energy were the literal only constraint, his body could have run on just his stored fat for 81 days straight. That is just a staggering amount of biological energy packed into the human frame.
All right, moving into Section 1, cellular respiration, slow motion combustion. So how do we actually access that massive reserve of energy? Well, we use cellular respiration. And chemically speaking, cellular respiration is literally the exact same process as combustion. Think about when you light a log on fire. You provide a spark that allows oxygen to react with carbon and hydrogen bonds, stripping them away into carbon dioxide and water, and releasing heat. Your body does the exact same thing with food and fat. But instead of a literal explosion of fire, it's a highly controlled, slow-motion combustion happening right inside your cells. And to understand this slow-motion combustion, we've got to look at one of the most poetic processes in the universe: inverse combustion. It all starts with step 1, photons from the sun. In step 2, plants use that solar energy to literally rip carbon out of the air and build organic molecules. Step 3, we humans eat those plants, or, the animals that ate the plants. And finally, step 4, we use that trapped solar energy to charge our ATP molecular springs. So literally everything you do is ultimately powered by ancient sunlight that was trapped by a plant. Mind-blowing, right?
Okay, so now that we know how the machine works, how do we actually program it to lose weight? First things first, we need to understand our base metabolic rate, or BMR. This is basically the energy your body burns just to keep the lights on. We're talking managing your core temperature, pumping your blood, running your brain. Even if you literally slept in bed all day long, you burn a massive amount of calories. In fact, a quick 30-minute jogging session on the elliptical, that's just a drop in the bucket compared to the massive amount of energy your body expends simply to exist. So, the absolutely crucial point here comes down to a simple mathematical equation. If you want to force your body to open up that fat hard drive, discharge the batteries, and breathe out those carbon atoms, you must maintain an energy deficit. The energy you expend through your BMR and your daily movement has got to be greater than the energy you consume through food. At the end of the day, it really is just an accounting game of molecular energy.
For his specific experiment, Karpathy aimed for a consistent daily deficit of 500 kilocalories. He did this by combining eating just a bit less with adding in some regular cardio. And mathematically, since 1 pound of fat holds roughly 3,500 kilocalories, a 500-calorie daily deficit should perfectly equate to losing exactly 1 pound per week, right? Clean, simple math.
Which brings us to section 2, the glitch in the data.
Because, as we all know, biology is rarely as clean as computer code. After meticulously logging every single calorie eaten and every single calorie burned on his smartwatch for 100 days, he discovered a glitch. His real-world weight loss was significantly slower than what that clean mathematical equation predicted. When he compared his expected mathematical weight loss against his at-home bioelectrical impedance scale, and then again against highly accurate medical DEXA scans, the numbers were just all over the place. The home scale completely disagreed with the medical scans. So what was skewing the data and hiding his fat loss?
Well, the first culprit was that annoying water factor. Remember earlier when we said glycogen, your biological RAM, acts like a sponge? When he ate carbohydrates, say a piece of pizza or a little candy, his body quickly stored that as glycogen. And that glycogen immediately soaked up tons of heavy water. This caused these wild, multi-pound weight spikes on the scale that totally looked like fat gain. But really, they were actually just temporary surges of pure water weight getting stored in his RAM.
The second culprit here was muscle recomposition. See, he was also doing resistance training during this year, so his body was taking the protein he ate and redirecting that energy to build heavier, denser muscle mass. Because he was building lean mass at the exact same time he was burning off fat, the overall number on the scale was barely moving at all, even though his actual physical body composition was radically transforming.
Oh, and by the way, here's a totally fascinating surprise detail about his data collection. To really get to the bottom of his body composition, he used DEXA scans, which rely on low-dose X-rays. Now, a lot of people worry about the radiation from these scans, right? But one scan exposes you to just 0.4 microsieverts of radiation. To put that into perspective, because bananas contain naturally radioactive potassium, getting a high-tech medical DEXA scan exposes you to the exact same amount of radiation as eating just 4 bananas. Crazy, right?
Okay, let's wrap this up with Section 3, the biohacker's diet, TLDR.
So putting the glitches and the math aside for a second, what was the actual practical application here? How did he successfully manage this human machine to actually drop the 30 pounds and keep it off over the course of the year? Well, here are the strict protocols he used to maintain that 500-calorie deficit without just completely going crazy. First up, intermittent fasting. He restricted his eating to an 8-hour window between 12 p.m. and 8 p.m., which just naturally helped control his appetite.
Next, he consumed absolutely zero liquid calories. We're talking no soda, no juice, no alcohol. He also avoided processed sugars completely. And here's a really great rule of thumb he used. He only shopped the outer walls of the grocery store, where the fresh meats and produce live, completely avoiding those center aisles that are just packed full of heavily processed foods.
Looking back at his entire year of biohacking, Karpathy beautifully summarized the journey from the cosmos all the way down to ourselves with this quote: "The photons power the fixing of carbon and CO2, which charges some molecular springs, which provide the oomph that fires the neurons and moves the fingers." It's just such a profound realization that the sheer biological wonder of our bodies is intimately, deeply connected to the physics of the universe.
Which really leaves us with this final thought. You are not just a person on a diet. You are a brilliantly engineered, solar-powered machine navigating this incredibly complex world of energy storage. Knowing that every single time you move a finger, or even just take a breath, you are actively discharging ancient solar energy. How will you choose to program your incredible human machine today? Thank you so much for watching this explainer, and keep exploring the amazing physics of you.